start our second talk today. It's my pleasure to introduce Lorenzo Diaz from Rio de Janeiro, who will talk about abundance of conservative and partially hyperbolic diffeomorphisms with non-hyperbolic measures.
Thank you. It's a pleasure to visit Poland during my summer. Visit Warsaw. Thank you for the hospitality. Well, my talk will be related to the talk of the previous week by Catherine, but this will be completely independent. And then the goal is to construct non-hyperbolic methods. I will explain what is this in partially hyperbolic conservative setting. We will see that is the title say there are many of that method. Everything that I am going to talk is a joint work with Diaz and Zhang from Niterói, Brazil, and Zhang from Beihaan in Beijing. Okay. One of the goals of my talk is that as you say in the talk of Catherine last week, but I will told you this will be completely independent. What I am happy here is to introduce a different tool, a tool that is different from the usual blender, that is what is the name of this? It's a completely it's mostly expanding property. Okay. Well, let me start with the setting. We will consider partially hyperbolic diffuse, which are defined in a manifold dimension at least 3. This means that we have a globally defined partially hyperbolic splitting with 3 directions. This direction is uniformly contracting. The direction U is uniformly expanding. And we have a direction in between. Well, the behavior of this direction is not clear. In some cases we have contraction. In other regions we may have expansion. But the expansion that we get are always dominated by the expansion of this bundle, and the same for the contraction. And the main hypothesis is that the central direction is one dimension. Okay, once that you have a splitting like this splitting depends continuously with the dynamics. Okay. The differentiability that we will need is, for many cases, we need using one, but this mostly expanding property. If you want to explore all the properties of this, we need to add some alpha. And we are mostly interested, but when the diffuse that we have preserve the revealness. Okay, we call conservative. This is the setting that we have. And then 2 comments about these settings. The first one is the existence of invariant foliations that come from the Hugh-Piusuk theory one foliation is tangent to this strong stable bundle, that is the strong stable foliation, and we have another foliation that is tangent to the stable bundle, that is the strong stable foliation. And well, this bundle is one dimensional, but we don't know in general if we can integrate the sum of this bundle. Okay. And then, well, when we have a central direction, we always can consider the central Lyapunov exponents of points of our methods with respect to log the f of EC. And then, well, two important properties in our case from this one dimensionality is that this Lyapunov exponent is just an integral. Okay.
Did I understand correctly that you assume that strong stable and center are integrated?
No. I just say something the contrary. Okay. I just told you that we don't know if these two bundles integrate the sum, integrate to a bundle. I just try to say exactly the opposite.
Okay.
And if these two bundles integrate to the opposite. But one important thing of all these settings is that this exponent is given by an integral. This, well, as the bundles depend continuously, this is a continuous function. And then if we have a sequence of methods that convert to some method, the Lyapunov exponents, the central Lyapunov exponents, also convert to this central Lyapunov. This is something that we will explore, or we explore in many settings. Another important consequences of these settings is, if you are interested, well, you say that mu ergodic is not hyperbolic. You know, hyperbolicity only makes sense for ergodic method. Otherwise, you can consider a complex combination and get if and only if this exponent is equal to z, the exponent corresponding to the central direction. But the general definition of a non-hyperbolic method is that you have some exponent that is 0, but here all the exponents coming from the bundle contained in the strong stable are contracting, are negative. All the exponents coming from this strong stable foliation are strong stable bundles, are expanding, and that means that if you are interested in some non-hyperbolic method, you only need to pay attention what happens in this central direction. Okay? This is a setting. And now let me go to some of the motivations. Well, one of the motivation is a motivation that comes from the 90s or late 80s. In that time, Jacob Pallis made many conjectures. About the complement of hyperbolicity. More or less, all these conjectures started having some, say, topological bifurcation test. More or less, the conjecture says, well, you have here the space of diffuse, So manifold or system, and then you have here a small region where you have some hyperbolic dynamics, say at zone A, no cycles, and then you are interested to know what happened in the complement. And well, the conjecture by Palin said that here densely there are cycles. Cycles, I don't, this is not important for my talk, but just today to make a figure of cycles means two types of cycles. You may have a saddle, and this saddle may have some non-transient intersection between the invariant manifold, or you may have another type of cycle, well, this is called tangency. You may have two saddles here having different types of hyperbolicities. Here we have a point with a stable manifold dimension 2 and another stable point with a stable dimension 1. And then these manifolds may intersect cyclically. And then this what Jacob Palin's conjecture in the late 80s. And well, this conjecture have many developments. I don't want to discuss this, but at some moment, I guess, I don't know, it's 2000 something, with Anton Gorodetsky, we make a conjecture to try to state. We make a conjecture in ergodic terms. And this conjecture in ergodic terms say that here, in the complement of hyperbolicity, where you have a non-hyperbolic well, I put it this way because if you invariant a measure for me,
non-hyperbolic measures.
well, non-hyperbolic, for me a non-hyperbolic measure is always ergodic, and for me ergodic is always F invariant. Okay. This means
Unlike
F invariant. Sorry. Well, this conjecture, as stated here, is wrong because there are systems. Let me do right here. Observation. There are systems. There are no hyperbolic systems. No, there are hyperbolic. Sorry, there are no hyperbolic systems. Yes, having only hyperbolic measures. Hyperbolic is also ergodic. And well, the examples of this type of methods are very degenerate. I think that the first example that I knew is an example due to Baladi, Bonatti, Smith. But once I gave this talk, and Pierre Berger complained bitterly. There are many examples coming from renormalization theory with this kind of properties. I'm not aware of this, but if you don't make, well, this is a conjecture. Say that is what you need to write this in a correct way. I don't want to do today, but what one expects is that in the complement of the hyperbolicity, you have no hyperbolic methods. Well, this is more or less proof. I part of the conjecture I prove with Gorodetsky, but there is a result due to Zhang, Croisier, Gang, where they prove this conjecture in, let's say, in a semi-local context. But I don't want to discuss this conjecture in many details. But what our results, the result that I am talking today, say, well, our result with Zhang and Beihaan. What is the ratio?
Yeah, this green plus is different from green.
This.
Yes, I think so.
Okay, no, it's okay. So, well, what we prove with is the following. Well, let me give some additional context. I guess that in the 2000, about 2000, Enrique Pujals, well, he didn't make a conjecture, but everybody who attended to his talk assumed that he made a conjecture during his talk. And then the people refer to this as the Pujals conjecture. That he said, well, if you look to the partial hyperbolic diffeos or partial hyperbolic transitive diffeos in dimension 3, do to dimension 3 and put partial hyperbolic, the conjecture of Enrique say that you have three types. One are the D that is you start with an Anosov diffeo in T3 and make a bifurcation to change the type of hyperbolicity of the point, of this point. There are, the other type are skew-products. As Catherine commented in her talk, essentially this means that you have a torus and a fibration by circles which is preserved. And then there is another third category, which are the flow type, flow type examples. This was Enrique didn't conjecture, but he discussed it. And then everybody decided to refer this as the Beihaan's conjecture, but this is especially unpleasant because the Beihaan conjecture is not true, and the Beihaan non-conjecture is not true. And very recently, there are many examples and this started a theory due to Bonatti, Autry, Bertaume, Hammer-Lindell, and many people. Probably I am forgetting names, but there are people who have tried with new types of partial hyperbolic diffeos, which are not in this class. And what is important is when you are in this class, this bundle, the sum of the strong stable and the central, integrate to a foliation, and the same holds for the second bundle. This is what the people call dynamically coherent, but these new examples are not dynamically coherent. And then when we prove with Zhang and Beihaan is the following. You have these three categories. In the three categories, you have the following situation. You have hyperbolicity, that in this case means Anosov. And in the complement, you have existence of non-hyperbolic meshes.
Where are modes made?
No, sorry. This is a very good question. I am now considering partially hyperbolic, 1 plus alpha, central dimension 1, and preserve the Lebesgue. It is more or less, you don't have this. And then, when when you have these three categories, that doesn't involve Morse-Mel situation, you have two possibilities. Either you are in the hyperbolic case, which are Anosov, or you have this non-hyperbolic method. You have two sets like this. Let me observe that clearly the property of having non-hyperbolic method is not an open property, while the property of hyperbolicity, as shown here of Anosov, is hyperbolic. This is the result that we obtain. Let me say they have something additional. Well, and now I will to discuss a little of philosophy here. Well, more or less the kind of system we are interested is, of course, we are interested in the complement of the hyperbolicity. Okay. We are interested in the complement of hyperbolicity. That is in the non-Anosov case. And then typically in this case, where you have is, well, you have a central contracting region and a central expanding region. And typically what happens is that you have some interaction between these two regions, and the interaction between these two regions is what allows you to get the non-hyperbolic method. But forget for a moment that I am talking about central contraction. If you are in a contracting region, to stay in a contracting region is very simple, because you have a kind of contraction, you are there, and you can stay in the contracting region as long as you want. But if you are in a expanding region, typically when you land in a expanding region, the region is repelling, and what happens is that the point is escape. And then the difficulty is how to make that point remain in an expanding region. For this, you need to be careful. Let me go a little. Well, to do this, there are essentially two ways. In a moment, I will state a theorem that is for us extremely important due to Gorodetsky, Ilyachenko, Klevsky, and Nansky. I will state the result later, but let me first go a little to the talk by Katrin. Last week, in the talk by Katrin, she talked about blended horseshoes. Okay? And blended horseshoes are exactly the type of object that allow you to stay in a central expanding region as long as you want. A blended horseshoe is something like this. You have a cube, but I will do the figure in dimension 2. Well, there is a third direction that I am killing. That is the direction corresponding to the strong stable direction. And then you have, well, indeed you have a cube, but I don't want to you have two regions. One region like this. And if you think only in the 2D dynamics, this map goes to the whole rectangle in an expanding way. And then you have another region where you maps also to the complete space. If you do the figure of a horseshoe in dimension 3, typically what you have is that a rectangle like this that maps in the whole ambient, and a rectangle like this that goes in the whole rectangle, and then in between you have some gap. Well, the key of Blender is, well, now you start with a strong stable lift. And then when this is a strong stable lift, if I take the image of this part, I will get another strong stable lift in the cube. Well, but you know, there are, in this case, you have a strong and stable lifts that, well, they are mapped outside the cube. This is more or less the technique that we use to get this central expanding region, and to get, well, we are not dealing with points. What we can say is that if you give me any sufficiently large, strong, and stable lift like this, crossing the Blender, well, you can get always some point in that strong and stable lift whose forward orbit stays always in the Blender. Here, you don't have this kind of condition. Well, let me now to say that there is a property introduced by Beihaan and San Marino. You know, let me say that at the beginning I thought that this property was more or less useless because it didn't give any additional thing to blenders. They use this to study minimality of foliations. And the property of blender, of Beihaan San Marino, that they call some hyperbolicity property, simply SH, is the following. Well, if you take any small disk in the strong and stable foliation, you can do the same thing for the strong and stable foliation. You have a point such that when you consider the forward iterations in the central direction, well, I need to put log here. This sum is positive, uniformly positive. That means, in words, that given any point and any strong and stable lift, you can find a point in that lift, so that when you consider, well, here I need to put Fn of x. When you look to the diagonal exponent along the orbit in the central direction of the orbital C, this point is immediately positive, expanded. But of course, when you have a blender, you have immediately this kind of property because you can simply add inductive. Well, and then what I will try to do.
Sorry, what is this sum 1 over n log?
It is the finite time logarithm. I am taking the orbit of the point, and I am considering the average of the Lyapunov exponent divided by n. And then if you want, you can put log the Fn of x divided by n. This log is uniformly positive. Well, you need to go to sufficiently large n, but it's the limit. Well, what is the proof of the theorem by Gorodetsky, Lachenko, Kreskalnatsky? I will state the theorem as they stated in their paper in 2005. But this is
this again, what is K? Klepsen?
This Klepsin is Gorodetsky, Lachenko, Klepskin, and Natsky. Natsky is an ex-student of Yuri Kiriachenko. I think that he wrote a pair of papers many years ago, and I think so far he stopped to do research. I don't know the other person, Anton Gorodetsky,
I met him in
Klepsing, I forgot
Russia.
his name.
Klepsing.
I don't know what is his first name. Victor Klepsing are, well, very well known. Well, what is the setting that we use? But I think this is you can state this in a much more general setting. They take a shape of two symbols and multiply by a rotation, and use in the rotation you get a map that is like this. And another map. If you don't want to be completely lazy, that this is an irrational rotation. But this is used to have an idea in mind because the result is open for, holds for open families of pairs. Then you need to consider things which are not rotation. Okay? And then they assume that three properties hold. I don't want to forget nothing. Okay. Well, I am changing my talk according to my lines. My God, this is not very good. Okay. 1 second, sorry. Okay, they assume to see one that existence of a contracting point I make this. They also assume a minimality of the FS. That means that if you take any point in the circle, then there is some choice of F0 and F1 that is dense in the manifold, and then 3, that is the most at the beginning little strain property, but is not that strain, is the following. If you take any point in the circle, you have that there is some I, well, in the case I is 0 or 1, such that x I prime of x is bigger than 1. This is the uniform contracting property. This is relatively, well, if you have an irrational rotation, this is more complicated because you need to replace this by some power, but essentially you can think that you have circles. In this circle, here the map F0 is expanding. Here the map F1 is expanding, and that means that you, for every point, you always can get a point that has the expansion. But this is the hypothesis of these people, and then more or less what we have is, well, in the practical term, well, the existence of some contraction, if you have some saddle where the central bundle is contracting, the minimality of the FS translates to the minimality of the strong foliation, and well, this is the most difficult property to find in practical terms, to get that you always have some expansion. What I did with several people, including Katrin and Michal, is to use these blended horseshoes. Another way that is more or less the same is to try to use this SA property, but what we made with Zhang and Jinghua is to use this mostly expanding property. In other words, what I am trying to tell you is that we are in a setting, well, I am telling you this, I state this for skew product, but you may have version of this for manifolds. But then what we will do essentially is, well, this mostly expanding property that in other cases, well, I didn't state the theorem of these people, sorry. The conclusion is that there is a mesa, an ergodic, non-hyperbolic mesa. Let me just to, I don't want to make a lot of comments, but let me say that this is a concentrated reference on the Dominique, Quebec, Bianca, Huatca. The mesa has zero entropy. And then what we will prove is, well, we see a way to implement this construction of Gorodetsky and co in our setting. And to implement that construction, I will try to use the mostly expanding property. And well, with this, we will get some results. And the very, well, I don't know, it's something that I don't like, especially on this paper, but it's like it is that here we have a kind of general theory that I will explain to you. And then, well, we need to see how the general problem applies in its context. And the problem is that in its context, we need to do a completely ad hoc proof, because we need to rescue all the properties that we have at hand. And well, one of the things is due to the, there is this stable ergodicity program of PUC and skew, and then thanks to this stable ergodicity program of PUC and skew, there are a lot of tools for understanding this system. And then you have a lot of geometrical, dynamical properties of this system, and then in each case, we will use different properties. If I have time, I will explain the case of D8, that is the simplest one, but we need to use a lot of properties of the dynamics. Well, 1 second, please. I don't know, I have something in section 2 to say. Well, sorry, 1 second. Okay. I will take a moment. I will erase it. Let me state, sorry, I don't know which is my page now. 1 second. Okay, we have the following proposition. Let me say our version of JEA. Well, essentially we need to repeat the proof of these 3 people in a slightly different context. You have M is compact. The dimension needs to be at least 3. You have a diffeo that is T1 plus alpha. Well, alpha is fundamental to use the mostly expanding property. You don't have alpha, you cannot invoke any of the properties of the. Well, there is a version of the result in the C1 topology that uses something that is called entropy expansiveness, but I prefer to skip this part. And then you have lambda that is also compact and a free variable. And we have that the four conditions hold. Lambda contains points of central contracting type. That is the central exponent is contracting. That corresponds to this property. The second property is that partial hyperbolicity with three bundles. This allows us to consider the strong unstable foliation. Let me put that the diffeo is here just to simplify my life. Okay. Well, you have two that FU is minimal in lambda. Every strong unstable leaf is of any point. No? If you take any point in the set lambda, the strong unstable foliation contains lambda, the closure. Okay? You can state this with lamination, but I don't want to bother you with this. This property mimics the property that is the minimality of the AFS. And then we have a third property that is mostly expanding, that I will explain in seconds. And this mostly expanding property is the property that will replace this situation. And then when you have all these things, I need some space for a conclusion here. Then there exists a non-hyperbolic method whose support is the whole lambda. Well, the most important part is that the method is non-hyperbolic. The fact that the method may have the full support is easy to do. And then let me try to explain what is this ingredient. As I told you, one of my goals is to try to promote this property in other contexts. They say that this is an extremely common property for people studying only if you try to study methods of partial hyperbolic diffeos. This is a super frequent property, but is very well suited to use in the conservative setting. And then let me explain. I have 15 minutes. The mostly expanding property. Well, to define the mostly expanding property, I need to make a small detour. Okay, I have everything. Well, first, you define what is a Gibbs U state. Before cutting at me is the Gibbs U state satisfy the Gibbs property. The answer is no. This is different. You say that a method mu is a Gibbs state. It gives you a state. Well, you take the disintegration along the strong unstable foliation. Here. And then you have here the methods in the leads, and you have that these methods are absolutely continuous with respect to the vector. Let me say that these U states are relatively easy to to obtain. You typically, when you consider limits or formal orbits, in this setting you have many, give you a state.
Absolutely continuous with respect to the bag of leaves.
Or leaf, of course.
So it is equilibrium for log differential around unstable. Yes?
I don't know if this is exactly the same thing. If you told me that it's the same, I am not sure about this. I think that the answer perhaps is not, but I am not completely sure why not. It is strange because all people that I asked about this, they never told me, Lorenzo, this is an equilibrium state. That is why I think that this is not an argument. This is never is the first person that has been about this. And then, well, and you say that this mostly expanding if for every mu in the family of give you states, the central Lyapunov exponent of this method is positive. But if you think a little about this, you more or less, this is not a proof, but what are you going to start to do? I need to make a proof with my hand because I am almost out of time. Well, you are more or less recovering a kind of SA property because you will consider a leaf, take some point, a measure, you take some point, and then this means that here, typically, you will get expansion. Well, there is a result to try to be a more complete due to Zhang, that they prove that these exponents, the proof is a little more stronger, are uniformly positive. If you don't only have positively upward exponent, you may have positively upward exponent that go to 0. And the argument for this is a kind of if you think that this is not true, you will take a limit and then you will obtain another measure that is integrate, and then you have something that has a some zero spot. I don't want to give you. Then this is the setting, and then the only thing that I can to tell you is that, well, you look to the proof of Gorodetsky and co, or to the proof of using strong the H property, and more or less you start to iterate some strong stable leaf. You can stay in the contracting time region the time that you want, but at some moment you decided to apply the strong, the most expanding property. That means that inside this strong unstable leaf, you can find some contraction, some expansion, and then you more or less use the same mechanism to concatenate orbits. So let me say two things. Well, there is a corollary of this. That is the following, is that if you have a diffeo that is in this category, I think that here you don't need to use Levé on this category. And you have that these two foliations are minimal, as in the top by Catherine. Then you have a dichotomy. You have either the diffeo is Anosov, or you have a non-hyperbolic And then you will try to see that you are in this category. And then let me say that this applies to many examples from the so-called anomalous examples. Well, and now I have still 3 minutes or 5 minutes. And then in these 5 minutes, I will try to try, well, I have 2 things that I want to say. Perhaps only one, I will have time for this. Well, let me say the proposition. That I guess is relatively easy. I hope so. You have lambda compact invariant. Okay. And then you have 2 properties. This is a few minima, meaning that every strong and stable leaf of any point of X, the closure contains lambda. And you also have mostly expanding. This thing implies that this is partial hyperbolic, 1 plus alpha, central equal 1. I don't need any additional hypothesis. And then when you have this condition, you have 2 possibilities of the system is Anosov. Then you need to prove that lambda is equal to n. Okay, in particular, or lambda supports some non-hyperbolic method. In the first part, we need to use a theory of Crobisset-Potier that I don't want to discuss. They are announcing, indeed, our preprint is waiting for the corresponding preprint of Crobisset and Potier, sorry. And then, well, you prove this how? If you say that is well, not Anosov, you have different possibilities. This is relatively well. You need to use this property, okay, to get this equality. But if you have that something is not Anosov, you have 2 possibilities. Well, if you have a method that has exponent equal to 0, you are done, because you have all the methods. And then, well, if you have a method with the central exponent negative, well, more or less, you will get some contracting point in the central direction. This is due to, well, you can use a cutoff like result. You precisely Crobisset and Gelfer have result about this. And then, well, once you have an exponent like this, you have periodic methods approaching to mean, and then more or less you are in the hypothesis. Here you have the point contains a point which periodic point which is the central contracting point. You have this property by free. This is part of the hypothesis. It is also a hypothesis. Then the next case that you need to do is, where is my eraser? The next thing that you need to do, well, this is very simple. You take, now you have the 2 exponents are positive. And you have again 2 cases. They are uniformly positive. Then Manet, the result by Manet implies hyperbolic, that this bundle is expanding. If not, well, you know that you have a sequence, a converging sequence whose exponent goes to 0. Then you have, as I started my talk, telling you that the Lyapunov exponents are continuous on the measure. You have that this measure has a exponent, but the point is that you don't know that this measure is ergodic. Maybe non-ergodic. Well, and then you consider the ergodic decomposition. Well, the ergodic decomposition, I know that by hypothesis all the measures are positive. You cannot have an ergodic measure whose 0 exponent is with 0 Lyapunov exponent, whose measure in the ergodic decomposition have all positive exponents. This is the contradiction. Well, and I will stop just telling that if you go to prove the DA case, well, more or less the proof started, you need to use a notion called accessibility. And then, well, you need to consider two cases. If the system is accessible or not accessible. Well, if the system is not accessible, then you have a result by Zhang that tells you that in this case is Anosov. If not, well, you need to start to use properties coming from the stable ergodicity progress. You need to see if the Lebesgue measure is ergodic or not. In fin, you need to deal with different cases, but again, it is relatively short, but I have no time to discuss this. Just to summarize, my goal is to try to tell you that, well, in many cases we use these I love blenders. They are very nice, but they are not available everywhere. And then there is a new ingredient that is this mostly expanding property that in many cases can can replace the use of blenders. I will stop here. Thank you so much for your kind attention.
I think the problem with this dips is an absolute continuity of foliations. You don't have, like for Anosov foliations, they are absolutely continuous. And here,
You don't know this.
You don't know.
Okay, thank you for the comment.
If you don't have foliation central stable.
Yes, I don't have this in general.
So even you don't have foliation.
Well, perhaps,
Well,
I think in many cases we have this central foliation.
No, but still,
But I think that is still.
continuity. So I think here is
Is a problem.
the difficulty.
Okay, thank you. Thank you.
Other questions, comments? So I wanted to clarify how exactly is your result related to this GIKN paper? Does it generalize it in some sense too much?
Yeah, the JK's paper was generalized, I think, in all directions. I think that this is one of the papers most important in my academical life, because, well, I think that first, you have many things. First, the first progress is that Nalsky and Klebsin extend this for diffuse. The first result was this for diffuse for skew-product, and then they extend for say, diffuse Anosov time the identity or, sorry, fiber by circle is the first generalization. Después I generalize with Lanto Gorodetsky for homogenic classes. I think that, well, we need to know hyperbolic homogenic classes, but the proof was more or less to repeat the argument. And then, well, there is a result, the result by Dominique and Waska, as I comment. They prove that this method has zero exponents, zero entropy, sorry, that this is very bad. And then, well, at some moment we knew that typically you have that that there are methods with zero exponent which have positive entropy in many cases, that this is a result that I. And then, well, with Ketrin, Michal, Jigwasa, many other people, we try now to use these ideas of Gorodetsky and co. to put, in more general case, having objects with positive topological entropy. You know, the result by Gorodetsky and co. is a result about limit of periodic method. You have when a limit of periodic method is a ergodic method with some properties. And when I study with Michal and Katrin and other people this year, many papers, is well, we try to do the same construction, replacing periodic points by horseshoes, to say, and that is well, this is a list of this. For me, this is a very influential paper. It's a relatively short paper. I think that is 7 or 8 pages. It's very simple. You know, I say very simple in the positive way. I don't want to say it well.
Thank you. Other questions? If no other questions, comments? Thanks, Lorenzo, again.
You go for lunch?
No, I need to
Is it
get on the
here?
way.
To co, trzeba iść gdzieś.